Here, welcome to edition number 139 for the Zoom Rock Room. It's been a whole month since we've seen you. We hope you had a good January after we saw you early in January and gave you a little vacation. And appreciative that some of you actually were worried if you missed the second Zoom Rock Room in January where we gave you a night off because I was doing a program. And I am going solo tonight. Renee is not feeling well at all today, so she's probably laying flat on her back right now uh, with medication. So if you need to mute yourself, I would appreciate that. So instead of me going through and trying to find out who isn't when it comes to that point. So anyway, uh, so I have a live story to tell you about how technology got into my way a few years ago. When I worked for York County Parks, one of the events I did every year, which I really love to do, was a Valentine's walk. February 14th, we meet at we'd have a walk at, mostly it was at Rocky Ridge Park in York County here, and no lights were allowed. We walked in the dark and we did fun games in the dark and some other educational things. So the one year I had a lot of stuff in my pockets, props I was going to use. So I took my car keys and I hid my car keys on top of a timber in a pavilion. So I wouldn't have to worry about losing them out in the trail because that would be just a catastrophe, right? So actually it was fairly cold that night. So when I got back from the hike, I had candy bars in my car for everybody. Valentine's Day, why not, right? So I get my keys off the timber, go out to my car, and I hit my unlock button on my remote, which you may or may not be able to see, and my car is not opening. It won't open. It won't respond. I was there clicking like it's not working. So I go back to the people. I told them to hang on. I got candy bars. I go back to them. I said, "I'm sorry. I can't get in my car to get the candy bars." And somebody said, "Did you try the key?" Which I, of course, did not. Well, I tried the key, and obviously it worked. And I found out that the remote was that's actually cold. Once I held my hand for a moment, it warmed up, and it got all working good and good. So anyway, yeah, technology got me on that one too, sort of thing. So let's start with our intro here. And things haven't changed too much since we last saw you a month ago with our sponsors. The Zoom Rock Room is always sponsored by Lair Architect in Lake Havasu City. Record high today out there today of 85 degrees. And as I mentioned, we missed Renee tonight. Not feeling not feeling the best. So Lair Architect is our major sponsor. And as we always encourage you to do, and some of you have done it, is email lairarchitect@yahoo.com and let Paul and Marcella know that you do attend the Zoom Rock Room and you appreciate it. And our contract comes up again for renewal in April, which is only about 2 months away. So anyway, just drop them a line and say hi if you would like. Buttonwood Nature Center, home of the Institute in Waynesboro, Pennsylvania. We had the executive director Tracy with us last Zoom room as an intro to bring you up to date on what's going on out there. A lot going on, and their fundraising is going quite well. In fact, they got a nice donation right after the her appearance on the Zoom Rock Room. We're not sure if it came from a member or not of the Zoom Rock Room, but she was just wondering because somebody was very nice about giving to their fundraiser. So, Educate, Inspire, Unite. They do have a Facebook page, and just announced. I didn't actually did not put it on in the program yet, but um, my May field trip, which is on May the 3rd, out of Buttonwood. We're going to take a bus trip to Schuylkill County and tour the number 9 coal mine in the morning and go fossil collecting at New Ringgold in the afternoon. So registration is now open for that. If you want to take a bus trip to the coal mine and fossil collecting, it's $65 for a member of Buttonwood, $70 for a non-member. So if you know somebody wants to go fossil collecting or you want to go along, we'd love to have you too. Last year it filled up very quickly for the program that we had scheduled. Retro Rocks in Lancaster, Pennsylvania, Columbia Avenue. Quite a unique store combining old-time records, vinyl CDs with rocks, minerals, fossils, gemstones. Uh, Steve Hess has it all. So if you're in the Lancaster area, stop by and see Steve Hess. It's like I said, it's a unique store on the west end of Columbia. Dirtman reports. Andrew's been quite busy with all the positions that he does have. He actually spoke to me yesterday and wants to be he'll be going to try to get back active into the Zoom Rock Room again. But always check out Andrew Rockhound on Facebook with his videos. The last one he did, he's that I do remember is the rocks that are at the Muhammad Ali training camp up at Deer Lake, Schuylkill County. So, Andrew, we hope to see him active again back into the Zoom Rock Room. Red Lion Telescopes. Wade Kraut has his showroom in his house outside of Red Lion in York County, Pennsylvania. Has anything from beginning telescopes, binoculars, right up to some professional models of telescopes. So Wade's always anxious to help people. He's into astrophotography. There's a couple of telescopes now that take really, really cool pictures, and you really don't need to know much of anything. It finds the objects for you, and you kind of treat it like a regular camera and get these fantastic pictures of galaxies and whatever else. Our schedule for the spring, this is up to some change. There are several speakers who are going to be scheduling some nights. So I'll be taking things out because a lot of them are me. So next time we see you in 2 weeks, which will be 2 days after the Daytona 500, gold in the Mid-Atlantic states. March, we'll talk about rock and mineral identification, how to identify some rocks and characteristics of minerals. March 18th, Renee is going to do a program for you, What's Good with Lichens and Mosses. And then April 1st, this is where you're going to come in because it says participants show and tell night. Okay, we expect you to have some show and tell things that you can show the whole room or send me pictures and I'll put it into a PowerPoint program to kind of keep it somewhat organized. April 15th, my 20 favorite sites in York, Adams, and Lancaster County. May 6th, we're going to have our first quiz night of the year. These will be for prizes from Retro Rocks. And May 20th at this point is What's New in South Mountain, Pennsylvania, which is the mountain between Gettysburg and Chambersburg. And there's some new interpretations, some new geology there that I've been
I'll just shoot her up a little bit.
actually learning about after I've been meeting with the geologist that did all the work. So that's our schedule. Like I said, it's probably going to change. A couple dates are going to change because people get back to me. Everybody want to mute yourself, please. Um, a couple programs I have coming up that you might want to participate in that you can. Uh, February 8th, that's this Saturday. February 8th, this Saturday already.
Can't do this.
I gotta see who that is. This Saturday, February the 8th, Perkins Restaurant in Hanover will be site where I'm going to be meeting with the Mason-Dixon gold prospectors. 11 o'clock about the gold in Southeast Pennsylvania and Maryland. Be at 11 o'clock. I think before, a month ago when I saw you, it was at 12. The time did get changed. And if you'd like to, if you're in the New York area and you'd like to sign up for the Ollie Senior Citizen Program, Penn State, York, it's a great program, by the way. I mean, loads and loads of classes for only a couple of dollars a year. March 4th, I'll be talking about the geology and the Gettysburg Campaign and the geology of York County Parks the first 2 Tuesdays in April. And like that. And Renee wants me to remind you that if you are interested in discovering how maple syrup is produced, as long as she's healthy, these are on Tuesday, Thursday, Saturday, and Sunday. Through I think February, she's going to be doing these programs, and about she'll be making a lot of maple syrup. I know in the next what next month or so, maybe more than a month now. So check Cador State Park out on their Facebook page. These are the times that you can go to the visitor center and see one of her programs. I talked about Ollie York last week. I did a program I've done on here featuring a gentleman named Atreus Weiner, or as the family tells me, it's Weiner, the York City school superintendent who became a very a very famous fossil collector with dinosaur footprints and trilobites in York. And in the course of the last couple of months, I got to meet Matthew Loser, who's married to a Weiner, and they wanted to see my big program about Atreus, so I invited them to come to the Ali program in York. Last Tuesday, I got permission of the director to allow them to be in the class, and there they are. All five of them enjoyed the program. I was a little bit nervous. I thought I was going to say something really dumb or not correct about Atreus because Matthew knows a lot about Atreus that I did not know. So, but they had a great time, and we had to get this family picture together, sort of thing. So it was like an honor to meet some of the family. All right, folks, here's the fun time. This showed up on Facebook this week, not from me. Elementary school, first grade. Supposedly Christmas at Wilson School in York, across from the York Fairgrounds, and we're gonna play a game. Yeah, we're gonna play a game. Where's Jerry? Where's Waldro? Where's Jerry on here? If I were you, I'd stay to the left of my cursor here. There's no boys over here. uh, so yep, I can name about every one of these guys, not the girls necessarily. But where's Jerry hiding? There he is, right there. I don't hear anybody laughing or gagging. Of course, I can't see either. So anyway, I thought that'd be a little bit fun. Uh, First grade, yeah, wow. So, all right. Stop sharing this. Okay. Wow, first grade. I can't believe I went that far in school. Hey, there's Andrew. How you doing, Andrew?
Good, sir. How are you tonight?
Caught you off guard there, didn't I? Yeah.
No, no worries. I do want to tell everyone I do have big news, and on the next Rock Room, I am going to share it. And I will invite all of you to join me. So, uh, yeah, big news coming soon.
We'll probably have a slide in the intro, right?
Yeah.
We can
And
put a slide in the intro. Yep.
and since the next Rock Room is on gold in the mid eastern states, why not see a Dirtman report on that? So,
That's true.
yep, I've got a couple of them, so might as well run one of those.
Okay. And like I said, this is being recorded and will be watched by Renee at some point in time. So wish her well here. It's a little sickness that she's had in the last couple of days. I know she hadn't been feeling good over the weekend too either. So she'll be back. She hopefully will be back with us on February 18th and all that. All right, move on to our program tonight. Been really looking forward to this one because our theme tonight is earthquakes. And of course, this one in New Jersey. Of course, we had a earthquake off the coast of Massachusetts last week, and maybe one near Sarasota, uh, New York, also. And I had the privilege to meet Greg Herman at the field conference for Pennsylvania geologists back in October. My first time. You might remember, you veteran viewers, he's been with us twice before, talking about the uh, impact craters, impact tectonics, I should call it, on Earth and the Moon. The two great programs. So, and Greg's a PhD, a structural geologist that spent 32 years in the New Jersey Geological Survey in the field and laboratory mapping bedrock and characterizing fractured bedrock aquifers. He now works with Trap Rock Industries and independently researches impact tectonics and other topics of interest. And his website, impacttectonics.org, provides links to his research, blogs, geoscience data, and virtual geological tools that are virtually free. So, yeah, check out impacttectonics.org is his website. Tonight he's going to talk about the Tewksbury, New Jersey earthquake that happened last April that some of you might remember because it was felt into eastern Pennsylvania. So, Dr. Herman, it's great to have you back again. Great to see you since October, and it's all yours. Oh,
Okay, thank you,
there
Jerry.
you
Appreciate it. It was a pleasure meeting you too. Um, Good evening, everyone. Um, yeah, this is my three-peat here. All
go.
right, so let me share my screen. Send request. I have to send a request.
Wait a minute. Go ahead now.
Okay.
I didn't do that.
And when you see it, let me know, and I'll start the presentation. Oh, sorry.
Now you're starting.
Okay.
You got her.
Let me see what's going on here. Okay, beautiful. Geological, geospatial, and temporal aspects of the 2024 Central New Jersey earthquake swarm. It's called the Tewksbury swarm by many. I'll show you why that isn't that accurate, but I'll also show you why geophysics is somewhat perplexing to me. As a structural geologist, I sometimes stray into adjacent fields when I want to do a deep dive on something that interests me. And in this particular case, having never experienced an earthquake before in my lifetime, and being a structural geologist and having lectured about them to students in my various college classes, I was rather pleased that this event occurred and this swarm occurred because I not only dealt with it in a virtual sense in modeling it, but I also felt it or heard it when I was home. But I'll go into that in just a second. What you see before you is kind of like the key to it all. That is the actual focus points of the different events, and not all of the events, mind you, because I only captured the first 200. This swarm is still ongoing. There are still events happening today, yesterday, last week. Very, very minor, drawn out, very low frequency, but nevertheless, it's still going on almost a year later, which is really, really quite remarkable since we really haven't experienced anything like this in the state before, at least in my lifetime or my tenure as a geologist in the state. I'll go into the details of this as we go on, but I've got a lot of slides to go through. And so a very focused swarm of light to very minor earthquakes began April 5th in parts of Hunterdon, Morris, and Somerset counties, as demonstrated here on the USGS NEIC website, which tallies earthquakes around the world and gives you very interesting metrics about them as well. So an initial 4.8 magnitude was actually preceded by a 2.2 a couple of days or a day earlier. But being a low magnitude event, we didn't think of that or view that as a precursor to this 4.8, which is one of the second largest events in New Jersey historically, and the largest instrumentally recorded. The only one that was larger was done before instrumentation and was done by hearsay and by the old time methods of how much shaking was felt and by whom and where. So the initial event was followed by hundreds of aftershocks. This is actually, again, a screen capture from the reporting page of the USGS showing that it basically reports earthquake events within a 30-day window. And there were 111 earthquakes that happened in 14 days. So that when this was happening, I was busy tallying this information up in a spreadsheet because after 30 days it evaporates and you can't have access to it unless you do a special search within the NEIC framework. All right. This is where it occurs in New Jersey. The swarm looks like it overlays the border fault between the Highlands and the Newark Basin, the Piedmont. It straddles the boundary, but I just want to point out that, can you see my cursor on the screen as I move it? Anyone?
Uh, no, I don't.
How about now? No?
No. Oh, yeah.
Okay,
Yep.
so the Ramapo Fault
Yeah.
is up to the north and borders the Watchung Syncline. These faults that separate the highlands from the Piedmont and the Newark Basin are called border faults, but they're not the Ramapo. The Ramapo sort of dies out and splays down into the Hopewell and Flemington. So this was actually overlapping a border fault, but not the Ramapo fault. And I'll show you that again in just a second. Um, I live here. The oval, which encompasses all of the events like this, has sort of got an axis which is oriented about north 10 east. I was out gardening that day when it happened, and I was startled because I heard a visible roar coming through the neighborhood. I was out gardening, so I didn't feel the shaking because I wasn't in an interior structure where things could move about. But I heard it, and it sounded like a freight train derailing. It was so loud. I thought, what in the world could that be? It's some kind of transportation event down on the road passing my house or something. And the birds were startled and everything happened. And then my wife opened up the door and said, we just had an earthquake. And I was like, oh my God, I just heard it. And I could hear it coming from the north, going to the south. So that was pretty exhilarating for me, having never really experienced one. So this talk has got four parts, really five parts, because of something that happened sort of in a postscript manner after I got done working on this the first time. I was awakened to the reality that my work wasn't really up to snuff insofar as I took a different approach to reach the same conclusion or a different conclusion than what seismologists reach. And I'll go into that. So I'm going to go into a brief review of seismology principles very quickly because I think we need to really establish the framework from which I'm going to launch into the details from. I'm going to look at the metrics of the 2024 Tewksbury earthquake swarm in a little bit of detail, and then I'm going to go into calculating fault sizes. Because what really spurred me into looking at taking a deep dive into this was my friend Mark Sadepsky got on the horn or emailed me or something shortly after and said, I was talking to a group and they wanted to know for me how big a fault this 4.8 event was. And I said, I really don't know. I haven't really investigated that kind of thing. I'll look into it. So this is kind of like what happened as a result of that. And then I want to take the swarm, put it into a regional tectonic perspective. And then at the end, if we have time and you guys aren't too bored, I'll go over how I was corrected in my approach and what the implications for that are. So, basic review of seismic principles. Geologists define the earthquake as the shaking and trembling of the ground caused by the sudden release of energy, which usually is a result of faulting in the subsurface, involving the displacement of rocks along fractures or structural discontinuities. Seismology is the scientific study of earthquakes. The elastic rebound theory states that rocks rupture when pressure accumulating in the rocks, in these elastic rocks, builds to a level where the elasticity is exceeded and it breaks. So the stored energy of the accumulated pressure is released as the rocks snap back into position, and the snapping back into the position is what generates the seismic waves that we measure on our seismograms. A couple of key points here is the epicenter. The things that we map at the surface of the Earth is a vertical projection from where the focus occurs in the subsurface at a specific depth along a fault. So keep that in mind because where you see the epicenters doesn't really correlate many times with where the faults are happening in the subsurface. And I'll show you what I mean by that. So earthquakes caused by the subsurface faulting or the injection of magma. Prior to rupturing, the elasticity and the tension builds up so that, like, if you were to think of it as a stick being bent because of torque on the ends, it reaches a maximum bending before it breaks. The material strength is exceeded and it snaps. Okay, so snaps back to its original straight shape. All right, so it's holding elastic strain, breaks, releases it, and generates seismic waves. Now, these seismic waves basically can be thought of in four different basic ones. Two body wave types, a compression wave where the material is forced together, closer and then further apart. So we have a pressure wave followed by a rarefaction wave. So pressure followed by tension. And then in the shear wave, we have a vertical displacement of material out of the plane. So shear waves move a little bit slower than P waves, which don't have any movement out of the XY plane. Then you get into the surface waves, which are the slowest but most destructive with respect to human infrastructure because they cause swaying at the surface. All right. So we get basically four different types of waves that we're dealing with that get recorded on seismographs or seismograms. Depends on who you talk to and what they call them. But basically, seismograms will record oscillatory motion along three cardinal directions: north, south, east, west, and up and down. Here's a seismogram showing the arrival of the compressional wave, the P wave. The S wave arrives shortly after, and then the surface waves arrive. I want to draw your attention to this particular seismogram because the first motion on the recording of the event is a downward deflection. So the first motion is downward here as opposed to being upward. You'll see some seismograms where the first motion is upward, and that's very important for earthquake analysis. So when we have multiple stations, at least three, we can determine where the epicenter is by measuring the lag time between the P and the S waves at specific distances. If we know what the dive time is, we can multiply it by a specific velocity to figure out what the radius of these circles are. And when we plot the circles around the listening stations, we get an intersection, which is the epicenter. Again, the projection from the subsurface to the surface of where the rupture, the center of the rupture occurred. Now, the Richter scale is something that we've always come to understand or to know because we've always referred to the magnitude of earthquakes according to the Richter scale, but that's been superseded by a new one that I'm going to go into in just a little bit. But first, I want to explain to you how the Richter scale was devised and why its limitations led to it being superseded by something else. So the amount of measure, the seismograms give you a physical measure, a chart of the energy released in an event in the form of waveforms. So what this Richter guy did, who worked for the I think University of California, Berkeley, I think it was maybe, or the USGS, I'm not sure at this point. What he was called on to do was because of the problem of earthquakes in California, he went out and he started measuring these things and looking at them with respect to the seismographs. And he said, well, we can quantify this. We can devise a scale. If we look at the amplitude of these S waves or the body waves, excuse me, and we then look at the magnitude of those compared to the lag time between the P and the S wave arrivals, and we can put the amplitude here on one side, and we can put the distance and the body wave metrics on the other side, and we can draw an arbitrary line between them and put a scale in between them representing a relative measure of the strength of the energy released during an earthquake. So this was the first parameterization of earthquake energy based on instrumentation, and it was adopted in order to try to understand California earthquakes. The problem with this is that it wasn't really scaled to take into account all size of earthquakes. It was kind of scaled to deal with the California San Andreas type of earthquakes. But what his scale represented was that each integer increase in magnitude represented about a 30-fold increase in the energy released. But the problem with it was that it involved a logarithmic plot. And logarithmic plots aren't really understood by the general public. And so his famous quote is, the logarithmic plots are a device of the devil, because it's really hard to convey to people sometimes what they mean. But nevertheless, he devised a scale that was used for many, many years to try to parameterize and rank earthquake energy releases. This was superseded in 1972 because Japan has big earthquakes and they couldn't really get the Richter scale to quantify accurately some of the energy being released from these huge events. So this Japanese seismologist came up with the elastic dislocation theory. It's called the moment magnitude scale. It's very similar to the Richter scale, but it's very different because it's the first mechanical approach quantifying the energy released by using the physical properties of the rock. So what he did was he devised, or he backed out an equation, the moment magnitude scale equation shown here, 2/3 log 10, the energy released minus a fudge factor. The fudge factor has to do with a regional variable, some heterogeneity or other thermal property that makes that region a little bit unique. Okay, so his use of this scale was based and predicated on this seismic moment. That is, how much energy is released from an area of known size given the known rigidity of the properties and how far the fault moved. Okay, so he quantifies for the first time the area and displacement associated with these faults producing these events using this approach. Also, as part of this dynamic earthquake analysis, because of the first motion studies, when you have a set of seismic listening stations around an event and you record where the first motions are, whether they're up or down, those give you a sense of this double couple, which allows you to plot the azimuth versus motion around the epicenter to figure out where the fault planes occur based on the separation of the pulls versus the pushes. We use stereo net diagrams in order to plot the azimuth and the direction. And when that is done, you end up with sectors that define two planes, one of which is the fault plane, and the other one's called an auxiliary plane because this is a non-discrete method for determining the orientations of faults. It gives you two solutions, one of which you have to decide upon which is the most accurate based on field observations or any other ancillary information that might give you some sort of an idea. But being geologists and familiar with stereo net diagrams, when you see a beach ball diagram like this, with compression sectors shown in black and tensional sectors shown in white, if it's a radiation type symbol that doesn't have any skewness to it, that means it's a pure strike slip fault. If it's something that looks like something you would plot from a number of structural readings on a stereo net, it means that it's a dipping fault plane, and you have to decide on which one, the auxiliary or this choice or this choice, is the correct choice based on geologic information and intuition sometimes. But if the black sector, that is the tension or the compressional sector, is facing up on these beach ball diagrams, it means it's a reverse fault, a thrust fault if it's a low angle. If the white sector is up, it means it's a normal fault. And these are the orientations of the faults. Okay, part two, the metrics of the Tewksbury swarm. Here's a seismograph recorded in Texas of the event. This all comes from the USGS NEIC, the National Earthquake Information Center site. And for any events over magnitude 3, they do the focal plane nodal analysis, the moment tensor analysis, where they figure out what the orientations of the faults are based on the metrics and the waveforms, like I was explaining to you before. So all of this information comes from the USGS. They give you the depth of the occurrence, 4.8, or the magnitude here, and they give you the depth over here, along with all the metrics, lat, long, and time of occurrence. Now, here's a shaking map that they prepared based on the reports online of people reporting the intensity of the shaking. Here are the solutions, the nodal plane solutions for the 4.8 event, followed by the 3.7 event. And they both have identical fault solutions, of which the north-south striking fault is the preferred direction, and the dip to the east shallow, in this case, actually 45 degrees with a strike of 011. The slip line is indicated by the rake, which is 158, which means that the material is moving up on a reverse fault like this. And the same is true for the 3.7. Now, for me, a structural geologist, this was like candy, because for the first time, not only do we have an earthquake in New Jersey, but it's an earthquake that I can put oriented faults into place in 3 dimensions relative to structural interpretations to see what the orientations, see if it fits. Okay, so this is I just want to go over something really quick. See, this shaking map is kind of biased because it really reflects the population density centers. If you notice the Philadelphia cluster to the south, the New York cluster to the north. So many people can interpret this as being that the transmission of energy was along this line, but that's not really the case. It's more north-south, and you can almost see that by the intensity variations within the map. This just shows you the population density centers as a base map. And it's very interesting that their little green moderate shaking isoline here has that same north-south orientation as the faults. So here's how I proceeded to do what I did and take a deep dive into this event. Every time an event was recorded, I entered it into an MSL Excel worksheet. I computed the elapsed time, the running time from the event, kept track of how many were occurring because, again, this was very exciting for me, having never experienced anything like this before. And I stayed on top of it, and I didn't go away until there were 200 events later. I charted these things up with respect to the earthquake magnitude versus minutes elapsed to see what kind of frequency breaks we were getting. High frequency events here that pretty much ended after this period of time here, which is this thing's in my way here. I can't see. Well, you get the idea. The depth versus the minutes lap. You see how the depth varies between successive events, between shallow, between 2 kilometers deep to 10 kilometers deep. Only a few exceeded 10 kilometers, down to 11 kilometers depth. The deepest ones occurred later compared to the shallower ones, and the higher magnitude occurred earlier compared to the lower magnitude. And then I did the frequency based on half-day intervals. You can see there's a frequency break after this. Uh, I can't, I have to actually get out of this to take. So 25 days. After 3 weeks, there was a big frequency break in terms of the occurrence. I charted it up in Excel using a scatter plot to show where the different magnitude events occur and to derive an ellipse that enveloped all of the epicenters to try to understand what perhaps the fault axial ratio is. Because most of these faults are circular, not square, and they're mostly elliptical, not perfectly circular. So I was trying to deduce some sort of constraining factors using these techniques in order to understand what was happening. The other cool thing about this is that if you take a look at the biggest event, the 4.8 here and the 3.7 here, all of the higher magnitude events occur to the east of the biggest one for some reason, which is very interesting. I'm not really quite sure why that happens, but if we look at also the number of events versus the depth, we see an average depth of 6.2 kilometers, a maximum depth of 11 kilometers. You start seeing some, cusped, sort of possible fault-shaped alignments of these epicenters, but it's really kind of like misleading because they can be at much, greater or variable depths. So you have to be very careful doing that kind of thing. Now, just to put this into perspective from a regional sense, the catalog that was done before of the earthquakes in the Philadelphia and New York City region in 2008 recorded 383 instrumentally recorded events, and I plotted those up relative to the depth and some of these commonly known metrics, like where you go from breccia, the cataclysite, to myelinite at the various depths and temperatures. And it's very interesting that the swarms, both the one that was recorded by the Columbia seismologists, the catalog of events over a historical time frame, they all seem to peak around 5 kilometers depth, right at the base of where you go from oil to methane window into initial metamorphism. So it's a good indicator of basically a rheological control in the subsurface between having saturated and slippery material versus more brittle material until you get down to about 10 kilometers depth and you start getting into the ductility where you get quartz plasticity and you really don't get that many earthquakes anymore because you get mineralogical creep as opposed to the breaking and the inducing of actual earthquake seismicity. So the Tewksbury swarm was most active during the first month. Highest magnitudes occurred early, the deepest occurred later. Highest magnitude events occurred behind, that is to the east of the initial and largest earthquakes with respect to fault slip directions. So looked like they were more focused in the hanging wall as opposed to the footwall. And the lowest magnitude events are focused in front of the largest ones with respect to fault slip directions. Now, this is where we get kind of crazy. I get kind of crazy, and so please bear with me. I think this makes a lot of sense, but again, it's not a traditional approach, and I just want to warn you about that, okay? Because of the moment magnitude equation involves the calculation of area and displacement, I thought as a structural geologist, I know that the displacement on faults is really pretty well constrained. And if I could constrain the displacement on faults to a factor that's pretty much common, and I know what the ellipticity of the fault is based on the distribution of the earthquakes, like a factor of 1.2 with a major minor axial ellipse, I can constrain the moment magnitude formula using those structural constraints to calculate the size of the fault area. And so I tried that, and I used an approach where I used the 1.2 elliptical size reflecting the distribution of the earthquakes in the epicenters. And from literature, usually you get about 1.5% slip versus the length of a fault. That's traditionally, I'll show you where that assumption comes from. Please note that the method I'm showing you again is not how professional seismologists calculate fault size. They use a different approach called stress drop. I'm going to go into that at the very end in just a little bit of detail, but I want to show you the comparison of the two methods. Here's an example of why these faults are probably elliptical, because the outcrop evidence shows that fractures form ellipses with elliptical terminations. The plot had an actual or an elliptical ratio of 1.17. The Google Earth plot of the epicenters had an elliptical ratio of 1.28. So I used 1.2 as the starting ellipticity for the faults. Fault displacement values are well compiled in the geologic literature. And here's the representative median value of 1.5% slip for strike length propagation of a rupture, based on Cowie Schultz's work in 92, and other people have done the same sort of thing. Therefore, since we know the magnitude moment formula, and I can substitute the area and displacement for the moment, since the moment is given by the USGS, all you have to do is do some algebra, rewrite the equation, and to deduce the area given the known constraints that I just showed you. Being an Excel nerd and growing up in the time of, or working during the time of Dilbert, where his famous quote is, "You can do anything with Excel, including land a 747." I basically programmed a worksheet to be able to experiment with the different variables in this formula to see how varying them would allow me to constrain the size of the faults versus the displacements. I plug in the moment from the USGS website. I use a traditional general value for the rigidity of the crust, and I start calculating the major axis of an ellipse, the radius of a circle, with the 1.2 being a slightly longer long axis than a circle. And I do this for a number of different calculations and magnitudes. And basically, I calculate that the magnitude 4.8 earthquake, given this approach and given standard moduli like this 3 times e to the 10 newtons, gigapascals for the shear modulus, I deduced that there would be about a 223 long fault radius. So roughly a half a kilometer, 400 to 500 meter long fault rupture from the 4.8 magnitude fault, given the regional F value of 6.03, which is used by the USGS and Switzerland seismologists. Now, seismologists in other areas like Japan will use these larger F factors, but I used the 6.03. And I deduced the 223 long fault. Now, what I did was I ran the different magnitudes through this calculator, because I'd always heard that one step integer in magnitude will result in a 30 times growth of the fault area. And sure enough, I computed a 31.6 size difference. On moment, 10 times variation in size of the area, and a 3.16 factor in terms of the displacement and the rupture length. And this 3.16 is so close to pi that it makes me wonder if it's just an error in my calculations from rounding. But it's a very interesting relationship. Excuse me. So given those constraints, A magnitude 4.8 earthquake would be about the size of 3 football fields put together. All right. Roughly, a magnitude 4 would be like 100-yard long fault, given this approach. The 4.8 down here to the right, using that F factor of 6.03, 3 football fields. I started using those metrics to do the modeling. I did the model using SketchUp Pro architectural CAD software. I basically entered in the maps. I generated the focal points by dropping vertical drop lines down from the epicenters. I brought in cross section CC prime here, which is from Drake and others state map cross sections. I actually constructed these cross sections for the state map. That was what I was hired to do. It's my job initially with the Geological Survey. So I'm going to take this CC prime section of it and compare it to the occurrences of the epicenters. And when you do that, the epicenters fall completely within the highlands along the trace of these faults that I projected from the surface into the subsurface. But this is not a true projection because it's not really looking along the strike of the fault. And when you do that, the alignment is really spectacular. The clusters fall within these fault blocks. Just it's almost spot on. It was really amazing and very relieving for me because having drawn the cross sections, when things fit like this, it was very, very satisfying. But please note that all of the epicenters, even though they appear to straddle the border with the Piedmont, are all falling within this 2 to 10 kilometer depth within the highlands. Previously fractured, foliated granites and gneisses that are multiply tectonized. Okay. So here's the drop lines. This is how I located the focal points relative to the epicenters. Now, the neotectonic perspective. Bear with me here, okay? 65 million years ago, when the Chicxulub impact hit the Gulf of Mexico, it created a whole new paradigm. And the North American and South American plates started rotating around the point of impact. And we've been rotating around that point of impact since 66 million years ago. And if you take a look at the motion of the vectors shown here by GPS measurements, the velocities increase as you go north because of centripetal force. We're right here. And so we're getting this constant motion of the plate drifting to the west until you get out here to the plate boundary and things kind of go haywire. But generally, uniformly speaking, we're talking about reflecting what happened 66 million years ago, setting up the neotectonic framework of where we reside today. Drift rates are now between 14 to 18 millimeters per year in the area that we're dealing with to the west. If we look at the GPS derivatives from the different stations around the area, and we look at the way the crust is moving in the vertical sense, we see that the Canadian Shield is rising as a result of eustatic rebound or isostatic rebound because of glacial unloading after the Pleistocene. This is the zero velocity line right here in white. So that when you come down into the Pennsylvania and New Jersey region, we're pretty much sinking at a very steady, slow rate, except for these little pockets that are rising in yellow. But everything else south of this line here, which basically is just into New Jersey, pretty much everything is sinking, okay? So I took the Sykes catalog from Columbia before all of this earthquake stuff happened recently, and I looked at it in detail. Here's his catalog. He's Columbia seismologist working with other Columbia seismologists. They identified the Ramapo trend and this cross trend right here. I did a little bit more than that by identifying seismic zones by actually doing density contours around the different catalogs of seismicity in the region. Here's the Ramapo seismic zone that's sort of like spawned on the Cortland intrusive complex right here in Cortland, New York. Here's the White Mountain seismic zone up here, probably spurred by these granitic plutons up here. Lancaster Redding seismic zone here, but you get the idea. And if you look at the way that the crust is rebounding up in Canada, there are these fingers that are coming down into New Jersey and Pennsylvania, less so, that are trending about north-south. So I drew on here to the right the Pollenskill Arch, where we currently have actively rising crust, as opposed to the Watchung Trunk, which is actively sinking. And look how the Watchung syncline fits in there very nicely. And the trends of the historical seismicity have the same trend as the faults in this swarm that is about north-south. This is the cross section showing you the depth of occurrence and how seismicity builds up around these igneous plutons, the Cortland pluton in New York, the Beamerville pluton in New Jersey, where we get seismic focused, I think because of the resistance to crustal shear. These plutons are coming up from the mantle and actually acting as pins to the crust, so that preferential resistance is being offered by these magmatic plutons as opposed to the regularly fractured crust. Now, the conclusions from this work was that the most probable faults are blind left lateral reverse faults striking about north-south, north 8 to 11 east, dipping 36 to 45 degrees east within Proterozoic basement. And if you look at where this swarm occurs relative to where these other events are happening, you can see that this one probably is just filling in a seismic gap, a historical seismic gap, and that we're probably going to see other swarms developed in the future to reflect the distributed strain that our crust is now experiencing under these neotectonic stresses. So this is a very compatible thing. Now, the other thing that occurred to me was that, okay, we have a pretty big fault that's occurring in the subsurface at about 4 kilometers depth. And if this thing reached the surface, we should see some sort of evidence of it. So I drove out there and, I talked to some people I ran into on the roads and freaked a couple people out because you're in New Jersey and anonymity is treasured, I guess. But um, the point is that I didn't see any surface expression of this on the roads, any cracking or anything like that that was anomalous. But the GPS stations that surround this all registered a positive uplift immediately after the event, which was kind of cool. Each station showed a rise in its GPS metrics after this event. Very subtle, probably, but I think that's probably worth studying more. So the summary from the work that I did was the 2-month swarm was most active during the first month. Highest magnitudes occurred early, the deepest occurred later. Highest magnitude events are focused behind the initial, the smaller ones in front, like I had said before. And then after all of that, shortly after that, a paper by Columbia seismologists was published in which they calculated a radius of 1 kilometer as opposed to 233 meters. That's 4 times the size of the one I calculated. And I said to myself, well, gosh, how did that happen? Why is that? Why would they get something so much larger? They even depicted it in brilliant detail here. This 2-dimensional fault slip inversion result, and their methodology was published. And I wrote Yang Won Kim, one of the seismologists up at Columbia, and I said, why would the discrepancies occur in the sizing of these things, given these 2 different approaches, when they're all based on the same, basically, theory and parameters? He goes, well, we use stress drop as opposed to the moment magnitude equation to calculate areas. And it's a very easy, straightforward calculation. And he went through it for me and he explained to me how he did it. And I looked into it and I did a little bit of a dive on this and I see where the common stress values in the region are anywhere from 10 to 100 gigapascals, and you can use the stress drop in order to calculate the fault area, but you have to assume some things like what the stress drop is, because we don't know what the stress drop is. We don't know what the slip amount is, and we don't know what the ellipticity of the fault is. We're using assumptions to make these interpretations. So I derived 223 meters. They derived something 4 times as long. And I said, well, wait a minute, something's wrong here. I have to be able to adjust something to be able to account for that. So I went back and I said, well, I'm using this shear modulus, the rigidity factor of the crust. What if this pre-fractured, this multiply fractured crust is much less rigid than we're assuming? What would be the result? So I went in and I calculated some stuff and I go, well, I'd have to have a 75% reduction in rigidity in order to get the type of long fault that they calculated using a stress drop. But when I did that and I went back and I calculated what the stress drop would be based on my original calculations, it's way too high. So my original calculations are probably wrong. It probably represents a minimum rupture distance as opposed to the maximum rupture distance. Okay, so there are other ways of determining the shear modulus. If you want to get into this in more detail, you can derive it by multiplying density times the shear velocity determined from seismograms to derive a value for the shear modulus. And I did that and I plugged it in, and things still aren't meshing. So in order to truly accurately measure the size of a subsurface fault rupture, one needs constraints on the magnitude of slip, the ellipticity of the rupture area, and most importantly, the rigidity of the material. Of all these variables, the least amount of testing has been done to determine the shear modulus of multiply fractured rock under deep confining pressures. Nobody does that. Nobody has done that. Nobody's taken rocks of variable foliation and fracture densities and subjected them to high pressure shear tests. I can't find any evidence of that anywhere in the literature. So, something to ponder regarding this research is how primary layering and secondary fracture decreases the rock's rigidity, so that when you decrease the rock's rigidity, the actual expression of the fault is much larger, and the stress drop is larger. So I'm still sort of spinning from all of this, to be honest with you, because when you take deep dives into adjacent realms of expertise, sometimes the realization, happens that, your approach is just wrong, or maybe needs to be refined a lot. um, Jerry, how are we doing on time? Because I have a 2-minute video that I produced that I'd like to run if we can do that.
Yeah, go
Is that
ahead. You're good.
all right? All right. So this kind of like is something I put together for 2 talks that I've done before, but it kind of like summarizes everything I said. And I should have probably just run this instead of rambled on for so long. But get it, enjoy. I'll cut it off there. Um, just to conclude, the results show that strike length of a subsurface rupture of a magnitude 4.8 event in crystalline bedrock could theoretically range from half a kilometer to over 4 kilometers, but it all depends on the parameters you use and the constraints that you use. And thank you, Mara, very much for your attention.
All right.
Should I stop sharing? Nope. Okay.
Hey, you can stop sharing if you want to, or
Okay.
we ask for any questions. Anybody has any questions, you may put them into the chat or verbally ask Greg those questions if you would like.
Makes my brain hurt, huh? You know, imagine how I feel. Imagine the consternation of saying, "Oh, it's so slick. I determined what the fault size is. No, I'm off. I'm off by a factor of 4. You know, or am I? That's the question. I really don't know. Things are so well. Geophysics. You know, fudge factors abound.
Different from the Dillsburg earthquake swarm that we had in York County, you don't have any diabase playing a role over there, do you?
Uh, I don't know. It's a good question. Um, I
As
do know those plutons exert a pretty strong control on the crust. If you look at where the Cortland pluton occurs, the Hudson River goes from very, very narrow to very wide, right at that nick point. And it's a pluton that is definitely incited local seismicity around it because of its resistance to movement and drift. So, and I think the same is probably true for Beamerville as well. So I don't know about the plutons in. I know something has to have sparked the Reading seismic zone. It'd be very interesting to take a look at that. See if it's Pluton related.
okay. Anybody else have any other questions?
Well, thanks, Jerry.
Thank you, Greg, for being back with us a third time. I believe this program was actually you and I discussed it in October when we were together at lunch at Pine Grove Furnace. So that's
Here's Dwayne's question. Do most earthquakes have one main event with many smaller quakes over days? I don't know, honestly. I think it would be very regional dependent. I think if you took a look at the 5.8 that occurred in Virginia, that'd be very interesting to compare this one to the 4.8 in New Jersey. Here's the thing that's a problem, though. When I started tallying up the metrics associated with this swarm from the USGS site, the metrics on the USGS site would change on a weekly basis. I would go back and the values that they entered for a specific event weren't the same for a week later, some of them. And I'm thinking, okay, so they're going back and they're refining their input based on maybe other seismic stations reporting something. I don't really know how they do it or why they do it. But if you go and look at the metrics of the 4.8 now, today on the USGS, they have a depth of 2.6 listed as opposed to 4.6. So I don't know what's going on there in terms of quality assurance, but it's not the most robust. I can tell you that because you're getting two different values listed on the same page at the same day, depending on what site you go on. I think it's a 4.6 event in terms of the depth, but it was a cool exercise. I do know this: if I get a better handle on the rigidity modulus of multiply deformed gneiss and granite, and it's a 50% reduction over that which is used on a normal basis, then that's, it would be really nice to be able to have some constraints on that, or at least, sort of approach a real solution to this, as opposed to say, well, it's in the ballpark of half a kilometer to 4 kilometers. But that's all we can do at this point. It's like just ballpark it.
We have a question from Larry. He wants to know what keeps earthquakes in the east from spreading further.
Well, I think we're getting it's not you mean spreading further west or what? Larry, I don't quite understand what
Well,
what you're trying to
Mike,
say.
you were talking about the fault plane ellipse where the earthquake took place. Uh,
Oh,
and I'm saying, like, why does it only go so far and not continue to spread further along the fault? I know there are places like, but in the West Coast, where you kind of like it's like a trigger and it'll travel for hundreds of kilometers.
yeah, that's called a runaway fault. And that's another aspect of seismology, that rupture dynamics, that I'm not really that familiar with, to be honest with you. Um, I really don't know. Not being a seismologist, I'm kind of like, again, sort of like, I took a different route to get to the same place, but when you realize from the locals that there's a much better way of getting there, it's kind of frustrating. But I don't know. I don't know. I know that the rock is we're dealing with a very distributed sense of strain. If you recall the way that the plate's rotating around that pole down around the Yucatan Peninsula, and you think about what the consequences would be. I've given this a lot of thought, being a structural geologist, and quite honestly, it's a mental exercise that's really, really challenging, because we don't know what the relative shear is between the crust and the mantle. We don't know. Is the mantle moving faster than the crust? Is the crust moving faster than the mantle? Um, I always assumed that you would have an outward diminishing gradient of velocity on material, because you're coming from the hot interior to cold exterior. So I always thought the crust would be moving slower than the mantle beneath it, creeping. But I don't know. Nobody does know, from what I can tell. And so when we're talking about these faults and what makes them, behave nicely and only propagate so far, it's just got to be the material itself and the behavior of the material. Being under a certain stress, and having the proclivity to shear in a certain manner. But quite honestly, we're just starting to understand these processes. And seismologists seem to use these ballpark estimates. Like they derive that 1 meter long or 1 kilometer radius of their slip by using a standard 10 gigapascal stress release. We don't know what the stress release was. It's just a guess, you know? But that's how they approach things. Is okay, if we use a standard approach here and a standard approach for all these, then we're going to get a relative sense of what's happening. But it's not a real sense of what's happening, it's just a relative sense. So does that make sense?
All
So much
right.
sense.
Okay. Well, thank you again, Dr. Herman, for being with us, and another inspiring
My
program
pleasure,
there,
Jerry.
um, for me to
Glad
work over
to be
anyway.
here.
Okay. In honor of Valentine's Day coming up in a week and a half or so, um, when do bed bugs fall in love? In the spring. You know, where do hamburgers take their dates on Valentine's Day? You probably never heard of this one, called the meatball.
No.
And finally, the last one. Hey, uh, what did the pickle say to its Valentines? You mean a great deal to me. I like that one. So if you're going to celebrate Valentine's Day, do it right. Have a great time and be safe about it. And as you know, I'm a big NASCAR person, so Valentine's falls on the Daytona 500 weekend this year, so be a tough weekend for me to be around. So okay, as we always remind people that this program's been videoed and will be on our new website, jonesgeo.us, in about 1 hour from now. If you'd like to go back and look at it again or tell your friends or family to check it out, jonesgeo.us under Zoom Rock Room. And of course, anybody that has any friends that want to join the Zoom Rock Room, of course, always free of charge. All we need is their email address. And we do have several people in here tonight that haven't seen for a little bit, or I haven't heard from for a little bit. So you guys, welcome back. You know who you are there. So we'll be back in 2 weeks. I'll be doing about the gold in the middle Atlantic states. Uh, as you're getting ready to plan for some summer excursions, perhaps I can tell you where to go to strike it rich. Till 2 weeks from now, be safe, be happy, and we will see you.